Welcome to Dhirendra Digital Solutions, your learning partner. Hello friends. Today we will be dealing with universal gates. Now when we say universal gates, we have basically two of them. First one is called as the NAND gate. NAND gate. Now what do we mean by NAND? NAND is nothing but not of and not of and. So what do we mean by not of and? Basically, first we have to do the AND operation and then perform NOT operation on it. That is what is NAND. So, if we look at AND operation, we will have two inputs, A and B. NOT is basically your complement, which is going to make a 0 into 1 and 1 into 0. So, if we are considering two inputs, then we'll have four combinations as 0, 0, 0, 1, 1, 0 and 1. Now, we have seen AND gate already. What is AND? If both the statements are true, only then the result is true. Otherwise, the result is false. Whereas 0 represents false, 1 represents true. Now, if both are false, when we perform AND operation, the result is going to be false, which means the result is 0. Now, what is not of 0? Not of 0 is 1. So, we get 1 over here. Similarly, what do we get over here? The 0 and 1, when you perform AND operation, you get 0 as the result, and not of 0 is again going to be 1. Then 1, 0, the output of AND operation will be 0, whereas when you NOT it, you get the result as 1. But when it comes to 1, 1 combination, the result of the AND operation is 1. The result of the AND operation is 1. Not of AND, that is, AND is giving you a result as 1. Not of 1 will be equal to 0. So this is the truth table of your NAND gate. Now, how do we go about writing the equation for this? Now, when we are writing the equation for this, we'll again start with our very fundamental way of writing the equation. Y is equal to 0 represents complementary state, 1 represents normal state. So we get A bar B bar dot 1 plus, here it is, A bar B dot 1, the output is 1, that is why we are writing 1, plus A B bar dot 1 for this particular combination. And the last combination is A B dot 0. Now, what will happen over here? Anything added with 1, we already know that it's going to be itself. So we get A bar B bar plus A bar B, because we have 1 over here, plus A B bar, as we have 1 over here, plus 0. So this equation I'll write it over here. Y will be equal to A bar B bar plus A bar B plus A B bar, because anything ORed with 0 is itself. So we get the equation as this. Now what we'll do is, we already know that if we have a particular term, I can repeat any of these terms any number of times. It does not make a difference in the equation. So this will be equal to A bar B bar plus A bar B plus A B bar plus, I will repeat this particular term because 0 plus 0 is also 0, 1 plus 1 is 1. We have seen it in the previous video. So I can repeat any of the terms. So we get A bar, B bar. I'm just repeating the term A bar, B bar. Now, what do we find common between these two terms? We have A bar into or dot B bar plus B plus, what do we have common over here? It is B bar into or dot A plus A bar. Now what will this be equal to? If I assume that B is equal to 0, then B bar is 1. 1 plus 0 will give me 1. Similarly, if B is 1, then B bar is 0. 0 plus 1 is also 1. So invariably this term becomes 1. So we get A bar dot 1 plus B bar dot 1, which is equal to A bar plus B bar. Now, this is not what we have defined. We have got the equation as A bar plus B bar. The derivation is perfect. The equation stands good with respect to the truth table. But as per the definition of the NAND gate, this is equal to, first we have performed AND, so A dot B, and then we have complemented the signal, so we should have written A dot B whole bar, or without brackets you can just write it as A B whole bar. Many a times for the dot which is being used to represent the AND operation, that will go missing. You'll just write it as AB, that is still acceptable. So here we get a term wherein we are writing by the definition of the NAND gate, we get the equation as AB whole bar, whereas by simplifying the truth table, we get the equation as A bar plus B bar. This is also our first De Morgan's law. This is our first De Morgan's law. Is that clear? The equation is A B whole bar. This is what we get as per the definition. And with respect to the definition, we have written the truth table. And with respect to the truth table, when we simplify the equation, we have got the equation as A bar plus B bar. Now, whenever something is in this form, it can also be represented this way. This is what is our De Morgan's law. Now, what is the symbol for our NAND gate? If I am making use of this, then we'll have AND. We're performing AND operation first, and then we are putting a vowel to it. We are performing NOT operation to the result of the AND operation. So we can represent it this way, wherein we have A and B. This is going to be Y. So this is what is your NAND gate. We also have this particular equation. As per this equation, first we are performing the complementary operation or the NOT operation, and then we perform OR. So this can be written like this, right? So this is my output Y, wherein I have my input A and input B. So this is called as bubbled OR, which is also NAND gate. This is NAND gate. Most of the times we use this particular symbol for representing NAND. This is rarely being used, but it is used, right? The next one is NOR gates. The next one is going to be NOR gates. Now, when we say NOR gates, NOR is basically not of or, not of or. So what we are going to do here, we are going to have two symbols A and B, because OR gate requires minimum of two signals, and the output is going to be Y. Now, since we are having two signals, we'll have four combinations: 0 0 0 1 1 0 1 1. Now, as far as the OR gate is concerned, we know that if one of the input is 1, then the output is going to be 1. If one of the input is 1, then output is 1. Otherwise, the output is 0. Now, what is the output for this? 0 ORed with 0 gives you 0. Not of 0 will be 1. So you get 1 over here. 0 ORed with 1 is 1. So not of 1 is 0. So you get 0 over here. 1 ORed with 0 is again 1. Not of 1 is 0. And 1 ORed with 1 is 1. And not of 1 is again 0. So this is what is the equation that we end with. Now let us go back to the fundamental way of writing the equation. So y is equal to, the first case, here we get A bar, B is also 0, so it is B bar dot 1 plus Z, this is going to be A bar dot B dot 0, output is 0, so we are taking 0, plus A dot B dot 0, this is B is 0 here, so we take it as B bar, plus A dot B dot 0, the last combination. Now when we simplify this, here whenever we add anything with 1, we're going to have itself, so it's going to be A bar dot B bar plus anything ANDed with 0 is 0, so we get 0 plus 0 plus 0, because we have 0 0 0, so these three terms become 0. So if I simplify this, I end up with the equation A bar dot B bar, or A bar B bar in general, what we represent it as. Now by the definition of the gate, this is not matching. So by the definition, we have A plus B, which represents OR, and we have complemented the result of the OR. So this is what is my NOR. By definition, we have NOTed the output of OR. The output of OR is A plus B, and we are doing the NOT operation on that. So it is A plus B whole bar is what we get as the NOR gate. But by simplifying the truth table, which was being generated out of the definition, we are getting the term as A bar dot B bar. So this is equal to A bar dot B bar. Now this is again our second De Morgan's law. De Morgan's law. Is that clear? So we have the definition as not of OR is NOR. We got the truth table. Then we have simplified the equation as per the truth table. We get A bar B bar. But by definition of the NOR gate, we get it as A plus B whole bar. And these two are equivalent. This is what is the second De Morgan's law. Now, how do we represent the NOR gate? The NOR gate can be represented as this, followed by a bubble, which was being used previously in case of NOT gate to represent your complementation. Hence, over here, the NOR gate can be implemented as OR followed by a bubble indicates the NOR operation. But by looking at the second equation, what we can do is we have got AND gate, we have got and before that we are going to not both the signals. So before feeding the signal to the AND gate, we have added a complement A and B. A and B will be complemented and then they are being added together to get the output Y. Both the representations are correct. Both the representations are correct. But by default, in most cases, we use this representation for representing the NOR gate. This is rarely being used. Is that clear? Please do comment, like, share and subscribe. For more related videos, log on to www.dhirendra digital solutions.in. The link is available below.